Hello, my name is David Whale and I'm going to give a talk today about building a wireless robot controller using a BBC microbit. You can find me on Twitter as WhaleyGeek. You can email me david@thinkingbinaries.com. And I work for a company called Thinking Binaries, and what Thinking Binaries does is they write firmware for embedded products. So that's the software that goes inside products you wouldn't know had a computer inside them. And I wish I could tell you about all the exciting things that I do, but unfortunately I've had to sign non-disclosure agreements with everybody, so it's all secret stuff, but it's all really cool. But if you imagine the sorts of software you can write for a Raspberry Pi or for a microbit, then if you write more of that and you write more technical low-level stuff, and then it loads into a product, and then you sell that product to someone, that's the sort of stuff that I do. Thinking Binaries is a sponsor of Pi Wars this year, and you'll also find me in the expert area where I'm giving a very tiny version of this talk. Start by saying a little bit about who I am and what I do. I've done some pretty large projects with the Raspberry Pi over the years. Some of you may remember these. In 2013, I built the world's biggest Raspberry Pi display, which was I think 12 meters by 7 meters display that was at Goodwood racetrack for the Green Power race finals. You may know my partner in crime, Martin O'Hanlon. We wrote a book together called Adventures in Minecraft, which is all about writing Python code to change the way Minecraft works. And I spent quite a few years being the official microbit wizard, so working with the Microbit Education Foundation and doing some weird and wacky projects. And some of these weird and wacky projects, in 2016, I was on TV with one show with a school called Valley Broom Academy, and we used 3 microbits together and a Raspberry Pi, and we controlled the Lovell telescope at Jodrell Bank, and we found a pulsar, which is quite exciting stuff. 2017, you may have seen me presenting at PyCon, and I was presenting the initial idea of Bitio, which was an idea that came out originally from my book as to how to do physical computing with the microbit and the Raspberry Pi together to control Minecraft, and I turned it into a standard package. In 2017 also, I did some work with the BET show at the Excel Centre, and we turned a Raspberry Pi playing pieces of music or musical notes and 40 microbits into a tone matrix. So each microbit represented one note on and off, and then the Raspberry Pi was linked to those 40 microbits, and you could turn the notes on and off and it would play a musical piece. And again in 2017 was a really busy year for me, as you can tell. And I did some work with BBC Click Live. They did a live stage show in Old Broadcasting House in London. And we had 200 microbits all communicating over the radio, communicating to my Mac on the stage. And we conducted the orchestra. And the best way to show this, actually, I think, is through some pictures. So here's the pictures of those. So you can see the book that I bought. You can buy it off of Amazon if anyone wants to learn how to code with Minecraft. And we have some microbit projects in there, and also all of the projects in there work on Raspberry Pi. This is the BBC Click project, where we had an audience of, I think it was an audience of 400, but we only had enough microbits to do the downstairs part. So that was quite good fun. This is the tone matrix, so it's actually 41 microbits. There's 40 microbits in a like a circle and in a matrix, and you press the buttons on the front and it turns the display on and off. And then the Raspberry Pi goes around and works out which microbits are on and which are off, and it will play a musical note in a sequence. This is the Jodrell Bank gig, so this is one of the world's largest radio telescopes, and we linked this up. It was 3 microbits talking to a Raspberry Pi, and the Raspberry Pi talking over the network to their control system. And actually, as you tilted the microbit, it would send commands to the Lovell telescope, and it would turn to lock into stars and pulsars. This is the big display that you may remember. That's on the Raspberry Pi blog. And this is me giving a presentation at PyCon. Now, there's something that links all of these. They all have Raspberry Pis and microbits involved somehow, and they all have a way of linking the microbit to the Raspberry Pi, so that the microbit is another device. And one of the great things about the microbit is it has built-in sensors, and you'll see that we'll be using that in this project. But I've written a package called Bitio, which I first presented at PyCon in 2017, and that gives you an easy way to just plug a microbit into a Raspberry Pi, write some Python on the Raspberry Pi that accesses the sensors and the display and other features of the microbit. Okay, so first thing I think I should talk about is the first attempt that we had in the club to do a robot controller. So this was the Stewards Academy Raspberry Pi Club. This was the first year that we'd attended the competition, and we had about a year lead in to doing the project, and we wanted a nice way of controlling the robot. We didn't want wires connecting it, we wanted a wireless way of doing it. And our limited research led us to suggest we could just buy a controller off of the internet and plug it in and it'd work. And pretty much that is the case. But one of the challenging things about our Raspberry Pi Club, which is the case for many STEM clubs, is that we're in a classroom somewhere that has no internet access. We're not allowed to have internet access. And unless we're really, really organised and prepare everything in advance at home, we turned up for a 45-minute club and we unboxed this shiny new controller, and it's all, git clone this, sudo apt install that, sudo apt get upgrade the OS. Even if we tether it to a phone, it could take us several hours to download the updated OS. So what we really needed was something that would just run on our Raspberry Pi. And we had quite an old Raspberry Pi. It was only a Raspberry Pi B Model 1, so one of the original devices. So we didn't want to spend a lot of time fiddling around upgrading it. We wanted to spend time building the robot, really. So we thought, well, how hard can it be? Let's make our own controller. What have we got in the cupboard? And we had a box of microbits that the BBC had sent us for the original rollout. So we thought, well, let's make something useful out of those. So the idea was to use 2 microbits. One of them would be used as the controller, and that would be battery controlled, battery powered, and it would send messages to a receiver. The receiver would pass those messages on over USB to the robot controller, which is a Raspberry Pi. There's a package already out there called Pi Serial that we had installed on our Pi, fortunately, and that would basically turn the motors on and off in different combinations and speeds to give us some traction. And the idea then was that you tilt the microbit, and what would happen is as you tilt the microbit, the robot would move in different directions. So we prototyped this, and like any good engineers, we started small and then added more features. So one of the kids in the club wrote a little piece of code for the receiver only. So you tilted the receiver and it was plugged in via the USB. We needed to check that link out first. And it would send a message, a single character, S for stop, F for forward, B for back, L for left, R for right. And then someone else in the club wrote the motor controller code, which turned the motors on in different sequences, and we managed to get the robot to move. That was great. And we managed to do that in one session of the club, which is quite good. It's always worth thinking with clubs, what can you do in 30, 45 minutes? Also allowing for, set up and pack away time, so that you've actually achieved something in the club. Next step was to then get it wireless. So the problem was, of course, is that we now got to walk around with the robot because we've got this USB lead. And while you can buy 10-meter USB leads, they're a bit of a pain if they come out halfway through. You're going through some maze or something. So then I left the kids at it, and they scratched their heads for a bit and worked out how to write the controller so that it would send messages, and those messages from the receiver would then go over the existing code they'd written to the robot controller. And that was another couple of lessons, I think, trying to get it to work, but that worked pretty well. And then we had a wireless controller for our robot. What we ended up with, interestingly, was a rather strange artifact in the receiver. So if you look at the code here, because the receiver was originally everything, it was the tilt sensing and it was the sending the message. When they'd refactored the code and split it apart, what they did was basically the controller would send an S to the receiver, and then the receiver, because it's got most of the original code in it, would say, if I see an S, I'll send an S to the Raspberry Pi, and that means stop, and so on for the others. So we ended up with this knowledge of how the control works in both of the microbits, and you see a bit later on that caused us a problem. But that was a side effect of refactoring the code rather than sort of throwing it away and starting again, really, I think. We did find on the day that it was a little bit jumpy to use, so the tilting, you'd tilt it and the thing would lurch forward, then you'd move it back because it was going too quick, and then it would lurch backwards, so it was a bit hard to control. But it took a bit of practice to get used to it. We spent a lot of time up in the up in the rooms upstairs practicing before we went downstairs on the challenge mats. It wasn't easy to change, so we could have changed things about sensitivity and about perhaps some of the commands. So it would have been nice to have different speeds on it. But because all of the logic about the commands was baked into both microbits, it meant to make a single change, you'd have to change most microbits. And that also meant, because of the way we built our robot, that the receiver microbit, which was plugged in with a really, really tiny USB lead, and was all had a case on it and everything, would have been quite hard to disassemble, and especially as there wasn't a lot of time between each of the challenges. So we just put up with being a bit jumpy basically. But it would have been nice to be able to customize it. And you'll see that when we look into the second attempt, which is what I'm presenting today, that it's now a lot easier to modify the code because we don't have this baked in knowledge inside the receiver about how the thing works. Okay, so here's the new design, and the new design is based on Bitio. So you'll see that there's a standard hex file that we load on the receiver here. There's a standard package that we load on the Raspberry Pi. There's a little bit of glue code, and you'll see that code later. It's tiny, but you always end up with a little bit of glue code when you write standard software. And then our standard code for driving the motors. And then over here on the controller, I've basically written the controller from scratch again because I wanted more control over the sensitivity and things. So it's got sensing, it's got some filtering on there. So there's a thing called dead zone. So as you hold the microbit and as you tilt it, you have to tilt it forward quite a bit and back quite a bit before it starts to respond. And that's just so there's a dead zone in the middle, so where the robot will stop. And that's quite important for the controllability. It's got a display on it, so it displays little telltale arrows so that you can, as the controller, you can see what it's doing, and obviously it does the radio transmit. And it's also got some button sensing on it. I haven't used it yet, but the idea is you can press the buttons and open a grabber or fire a Nerf gun or something like that. But pretty much from this line here to this line here is all standard. So it receives a radio message, and the radio message pops out this other side, and then the glue code just decides based on that radio message what way to turn the motors. And so all of that is standard. You don't have to change the receiver whenever you change any of the controller code. And you could have multiple prepared controllers with different settings in them and just turn one off and turn another one on. I wouldn't recommend you have more than one controller running at the same time. That could be like a bit of a tug of war between people, but you can have multiple prepared microbits. So you could have someone upstairs in the workroom, perhaps tuning the sensitivity of the controller while someone is actually using the robot. So that's quite an interesting design now. Okay, so now to the demo. This is where things always go wrong, isn't it? Okay, so I've got a demo program here which glues everything together. And I've got a microbit here that's already loaded and transmitting, and I've got a microbit here that will have Bitio connected to it, and I've got a USB cable. Now, one of the biggest problems sometimes is working out which serial port your microbit is connected to. So this just uses a standard feature of Bitio, which is what it does is it scans the microbits. So you just follow the instructions. Make sure there's no devices there, press enter. There's a scan of the system. Found 132 devices because the Mac's got loads of virtual devices already. Plug the USB cable in. Wait a few seconds, press enter again. Does it after that scan? It's found 133 devices, so one of them is new. So it differences the lists and says, well, the one that I found is TTY USB modem 1412. I never could have guessed that, if I'd tried. So press Y. That now remembers that, and now the program runs. And you only have to do that once. You never have to do that again if you don't, unless you change the USB port, and then it will scan again. So that's quite nice. And it's the same on the Raspberry Pi, and it stores the serial port inside a text file. So if you do actually know that it's on the Raspberry Pi, it's TTY ACM0, you can just type that in the text file, and it's all set up ready. So you never need to actually do that on the day. So now I have my microbit, and let's try and do this so you can see what I'm doing, so that I can see what I'm doing as well. So as I tilt the microbit forward, the robot goes forward. As I tilt the microbit backwards, the robot goes backwards. If I put some extra tilt into it, I tilt it forward and to the right a bit, I can do some lovely little tiny turns, little swirls. Do the same the other way. I've got quite fine control over it, really, really fine control. There's an added mode in this simulator, because the simulator is made of Pi game. I put like a little force field around it, so if you hit the main wall, it just bounces back, just like a real robot. It would actually bounce off the wall. I can go backwards, and I can go forwards, and I can tilt. And then obviously when I close the program down, so I just Control C in this window here, then that window disappears. And that's it basically. So you'll see on the microbit itself, it's got these little arrows. It's quite hard to see on the screen, but the arrow is dependent on which way you're tilting it. So that as you're getting used to these, especially in a competition environment where you've got maybe 6 people in the team and they're all having a go, it takes a little while to get used to the controller. And what's quite useful about this is it actually has an image on the display. It was a dot in the middle when it's stopped, and that's when it's in the dead zone. And that really is just to calibrate the user, really, so the user knows what they're doing while they're getting used to the controller. But all the settings in here are configurable by just changing numbers in the code, so you can change the sensitivity yourself. Okay, just to finish off, let's have a little look at a couple of the design aspects. So here's the internal architecture. It's basically, it's Bitio does all the hard work. That's got PySerial built inside it. There's a file called rcontrol.py, which is all the actual controller code, the glue code. And then demo is basically is where you put your code, and this is it. This is the code that you modify. So you sense the controller, and you get a gear, a speed, and a direction, and you just basically call functions that control your robot. And then I've got a robot.py, which is a simulated robot basically. So you throw that away and you put your real robot in there. So you can attach it to any motor controller is the idea. The sensing basically has a dead zone, so if you imagine the X and the Y tilt, then I think it's 100 or 200, so anything in this region won't move the robot. And then this is me just working out the various corners so I can send the right message. And then the display, so this is, again, I like sketch things out on paper, so this is me designing all the little icons for the display and working out what numbers they send. There's 9 different positions. And the last bit that's worth looking at is the radio format. So I came up with a standard message. So it starts off with an RC to mean remote control. So if you were if there are other microbits sending radio messages and you didn't want them to interfere, what the receiver does is it ignores anything unless it starts with RC, and you can change that unique code. There's a sequence number that changes by 1 every time a message is received. That could be used to detect lost messages, for example. So your robot could beep if it's out of range. Then it sends the A and the B button, so you can press a button and it will sense the buttons to open a grabber or something like that. It sends the gear forward, stop, or backward. Sends the rate or the speed, so it's a number in the range from 0 to 99. And then it sends, it's a signed number, so plus or minus, it sends the steering, the direction, so from minus 99 to plus 99, so you've got quite a lot of control over the steering if you want that. I originally was going to put checksum in, but I didn't bother. I thought I don't actually need that. And that works quite nicely, and all the code's written for that. It's all in GitHub. Joining two motors is really simple. I basically said change this in 4 places in the code, in the demo, and Robbie is my simulated visual robot, but you basically just control your motors in there. And to set up, basically you go to GitHub, you press the code button, download a zip, unzip it, and then you run the demo.py, and it all just happens as I do. Okay, so that's pretty much it. You can get the code from github.com, WilyGeek Robot Controller. If you have problems or anything, you can, probably the easiest way is to log a GitHub ticket, and I'll always answer questions on there when I can. And it'd be really nice if someone picked this up and did something with it, try to control their robot with it. Buttons A and B would be quite fun to get working if you wanted to have a go at that. You can also transmit radio messages back to the controller. So you could get the Raspberry Pi or Raspberry Pi robot could send a message back to say what its battery life is, for example, and it could display that on the controller screen, which would be a really fun way of doing it. You could have more than one controller, but that would get a bit interesting, I think. And if you decide that microbit radio control is not the way forward, you might want to go and see Martin O'Hannon's talk, and he's doing a talk about Blue Dot, which is a way of doing the same sort of thing from a smartphone. And that's pretty cool as well. I must admit I quite enjoyed doing the microbit because it's something we could build from scratch in the club, and we had all the skills to do it. I find the Bluetooth a little bit tricky sometimes to get working, but Martin's done all the hard work of getting the Bluetooth working. Okay, so if anyone's got any questions, please ask them now. You can always contact me via Twitter. You've got my email. Twitter's probably better actually, or if you've got a specific question about the code and you want to try it out and you're having problems or whatever, or you've got ideas to change it, GitHub Issues is the best way to get in contact. Thanks so much and hope this talk was interesting. Bye.